Hi everyone, today I would like to make a video about how to contribute a model to the Hugging Face Transformers library. So as most of you know, the Hugging Face Transformers library is a software library, a Python library that recently crossed 100,000 GitHub stars, and it's used for state-of-the-art machine learning. So you can use it for all kinds of algorithms that are based on the original transformer, which was developed by Google in 2017 and which is also used for models like ChatGPT nowadays. And so, the Hugging Face libraries, so Transformers is one of them, but actually there are many more. But in this video we're going to focus on the Transformers library. We can actually see all of the code because it's all open source. So you can just go to the models folder here, and here you can see a overview of all of the algorithms, all of the models that are implemented within the Transformers library. And so it all started with the BERT algorithm. And so as you can see, for every model that is available in the Transformers library, there's like a lot of files. As you can see, there is a configuration file, there is a modeling file, there is a tokenization file, and so on. And so basically when you want to contribute a new model to the library, to the software library, the goal is to just have a new folder here with a new model, and then all of the scripts implemented that are required for that. And so in this tutorial, I would like to go over the steps. So I wrote down the steps that I usually take to contribute a model to Hugging Face. And so we're going to do them one by one, and hopefully we'll end up with a new model in the Transformers library. And so for this tutorial, I'm gonna take a look at the Dino V2 model from Meta AI. So Dino V2 is a self-supervised vision transformer model. So let's quickly look at the paper. I think last year there was another paper from Meta, which was the Dino paper. As you can see, it has quite a lot of citations, more than it's now 1,500 citations. And the reason why it got a lot of traction was that they developed a new self-supervised learning algorithm to train vision transformers on a lot of images without any labeled data. And then they saw some interesting properties after training them. When they visualized the attention, you could actually see that the model learned to like segment objects within an image without ever having been trained to do so explicitly. So as you can see here, so they take a standard vision transformer model, they have their Dino method to train it on a lot of images without any labels. And then after training, they could just take an image and then visualize the attention that the model was paying on that image. I think they visualize like the attention to the special CLS token. And as you can see, the model is like capable of recognizing the individual objects within the image, which is super interesting. Like here is, for example, capable of segmenting the individual animals. And so this Dino paper is a really nice paper. It was also, the first one was also open sourced. And I also actually ported this one to Hugging Face at the time. And funny enough, currently if you go to the models tab of huggingface.com, you will see that Dino has like the most number of downloads. But I think, I'm not sure actually, it's a lot of people that are using it. It might be that there are just a few people downloading the model a lot of times. So in this tutorial, I want to go further with Dino V2, which is like an upgrade of the first Dino paper. So I've downloaded the paper here. It's quite an extensive paper. Again, they show these visualizations of the attention. Well, they are using principal component analysis to do these visualizations, which is pretty interesting. And so as this model is like a very standard model, I thought it was an ideal model for like showcasing how we can add this one to the Transformers library. So let me maybe first go over the steps that I usually take when adding a model to the transformers library. And I think I will just do the first step in this video, and that's running a forward pass with the original implementation on some dummy input data. So yeah, when you want to like contribute a vision model to the transformers library, then what you could do is like just take a very simple image, like a cat's image, which I usually actually use. I think it's even in this script here. So yeah, this is like a super simple image that you can use to like forward it through the original model of the original implementation, and then I also forward this cat's image through my implementation, and then I simply compare their logits, which are like the unnormalized scores that these neural networks give as an output, or their hidden states, and then you can like really see whether your implementation is returning the exact same thing as the original model on the same input data. So that's always like the first step that you need to do if you want to contribute the model to Hugging Face. Yeah, the steps that are coming after that, I guess I can go over them in a future video. But so in this case, let's go over like running a basic forward pass on some dummy input data. So for that, I'm gonna go to this GitHub repo that they open sourced. And then the first thing that you always need to do is you need to fork the repository. It's possible that I already done this. But yeah, the first thing is like creating a new fork. So let me quickly do that. So then what you basically do is you create like a copy of the repository, but under your own username. But this is still just available on GitHub. It's not available like locally. So then the next step you need to do is click here, and then you need to like locally clone this repository. You can either use HTTP to clone it or SSH, but in this case, let me use HTTP for that. So then I'm gonna go to my terminal. In this case, yeah, I'm on a MacBook, but it would work equally on a Windows machine. So then I'm going here to my Python projects folder, and then I simply do git clone, and then you can copy paste this URL here from here. You can just copy paste it, and then it says that it already exists. Yeah, this is because I already cloned it. So then yeah, after that you can just do cd and then the name of the folder. So I think in my case it's Dino V2. And then you can, well, in my case, I can just do code and then the dot, and then it will open in VS Code. So VS Code is like my favorite IDE to develop in. VS Code is freely available. You can just find it and download it. And then, yeah, you can like have this code command, which I use, which is explained probably in this thread. But this is very handy because it allows you to, well, do what I just did, just code and then the path to a certain folder. So in this case, I just want to use the current folder, and then it will open in VS Code and showcasing all the content of that folder. So in this case, we are in the Dino V2 folder. And so, yeah, the first thing you always need to do is to run a forward pass on some dummy inputs. So for that, what I usually do is I create a new script, like a new inference script. So let's call it just inference.py. And here we're gonna like load our cat's image, for example, then instantiate the model, load the weights of it, and then run a basic forward pass. So let me quickly go back here to the Dino V2 repository. So yeah, one thing you will definitely need to do when you want to contribute a model is like getting familiar with the code base of that particular model. So in this case, for example, they open source some checkpoints, which is of course needed because yeah, we only like add models to the library if there are some pre-trained weights. Otherwise, there's no chance of getting it merged. But let me quickly go to their folders. So here in this case, they have models folder and then vision transformer. So this is probably defining the whole model, Dino vision transformer, as you can see. And then yeah, they define these various variants, like a base-sized version, a large-sized version, even a giant version, which has like 40 layers and so on. Okay, and so the model implementation itself is available in the models folder. All right, and then they probably provide some main.py scripts, setup.py scripts. Well, they probably provide some script to train it or to inference. Well, yeah, they also provide them already on Torch Hub, which is pretty handy. But yeah, it's not the Hugging Face API, so we're gonna make sure those models are available in the Hugging Face API. But here they say, okay, you can do logistic regression, linear. Okay, train.py is available in Dino V2 run train.py. Dino V2 run train.py. Right, and then here are they instantiating the model? Doesn't seem like it. From Dino V2.train import main as train main. Okay, .train import main. Train.py. Okay, so this seems to be like the whole training script. And then probably here they are somewhere instantiating the architecture. So here they say SSL mid architecture, and then they put it on the GPU. Okay, let me check what this SSL mid arch thing is. Okay, it defines like a gradient scaler and so on. Looks quite complex because yeah, it's using a student teacher setup, the whole self-supervised method. Okay, but we probably don't need all of that. We just, well, the model itself is available in the models folder here. So what we probably need is like from Dino V2 dot models import. Well, let me go to the models folder and then, okay, so they have a built model, and then okay, so they import vids, and then they say teacher and student. Okay, so here we have these various models. Yeah, actually I can just do that, I guess, and then so they have a vid based thing, and then it will return a model from Dino V2.models. Well, yeah, previously I was already looking a bit into the repository to see like how I previously created a Dino V2 model. So in this case, well, I think I can just do this from Dino V2 and then the models folder, and then, well, it's actually in the vision transformer script, so maybe I should do it dot vision transformer, unless I use the build model function directly. But yeah, this is gonna return student teacher things. I don't actually need them, so I can just do like this. And then let's maybe print out the names of all the parameters. So I'm just gonna go to a new branch here. So for that you can use the git switch c command, and then you can say, okay, let's call it understanding Dino V2. I'm gonna git add, which means I'm gonna stage those changes that I made to the repository, and I'm gonna commit them. So committing means like creating a snapshot. So let me say add inference script, and then I'm gonna just push this to GitHub. So this is to my fork. So basically, if you push this, you will see it appear in your fork. So the fork that we created, maybe I do have an internet connection issue because it's taking a long time. So yeah, I git cloned Dino V2 here. And as you can see, it currently only has a single branch main, but so now I created this new branch understanding Dino V2. Yeah, it was not able to push because of my internet issue. Still gives me, wait. And this should now work. Permission, oh yeah. Wait, this is not my fork. Okay, so that was the issue. So yeah, I actually was git cloning here. Oh yeah, right. So yeah, this Dino V2 folder here that I already have is referring to the Facebook research repo and not my clone of it. So let me just call this one official. Let me go back to the Python projects folder. And then I'm gonna do git clone, and now I'm gonna git clone my fork again. And I'm gonna go to my Dino V2 folder, and I'm gonna open it. So, and here I'm gonna add this inference script. Then you can do from Dino v2.models.vision transformer import. So let's go back to their models folder, vision transformer, and then you can, well, let's say we want to have the fit base here. Model equals fit base. Does it take any arguments? Patch size, keyword arguments. I'm not going to provide any arguments for now, and I'm going to print out all the parameters. And I'm going to move to a new branch. Let's call it understanding Dino V2. And I'm going to add and commit those changes. Add inference script, and then I'm gonna push them to my fork. Sorry, git push. Yeah, understanding. So you always need to provide a name of the repository on GitHub where you want to push to, and then the name of the branch. And so in this case, this is called origin. This is like if you type git remote v, you can see that the origin refers to my fork. And then typically you also can add a upstream repository, so that would then refer to like the official. Yeah, now as you can see, it has appeared on GitHub. You can always add a upstream branch, so let's do that. The upstream one is like the official Facebook one. So now we have like two repositories on GitHub, which we have called origin, which refers to our fork, and then the upstream, which refers to the official Facebook research. So if I do git push origin, it will push to this repository on GitHub, which is my fork of the official one, and then you can specify a branch name like Dino V2. So this has now been pushed. So as you can see, it will just have added this inference script, as you can see right here. So then the next step, well, I'm not gonna install PyTorch yet another time on my local laptop. So I think I already had a Dino. No, I don't. Let me add a Dino V2 folder. And then I'm gonna create a new Google Colab notebook. And then usually what I do, of course, you can do all of this locally, but oftentimes I don't want to deal with the hassle of setting and installing the whole environment for one specific model. So in this case, let me just create a setup environment cell. So in this case, I usually type this, then I do git clone the branch name, so understanding Dino V2, and then the URL of the fork. Sorry, yeah, it was just this. Okay, so I've cloned it, and then let's see if we can go to the Dino V2 folder, and then I can just type inference.py. The reason we have to do these weird things here is because, okay, it's complaining, but okay, it seems to print out all the parameters. And as you can see, it's super standard transformer, a super standard vision transformer, so it consists of a patch embedding layer, as you can see here, and then you have these blocks. So a standard transformer consists of typically 12 blocks, which you can also see here. We have 12 blocks because we're starting to count from 0. Doesn't seem like this model include any classification head on top, it just adds a layer norm after the transformer. But yeah, this is already nice because yeah, we can like see all the names of the parameters of the model. We can see their shape. And so for that, you can just do this. Now, of course, we want to like do a forward pass on some dummy input data, like a image of a cat. And then we want to see whether the model predicts certain class like cat. So for that, we need to equip the model with weights. For that, well, let me go back to the Dino V2 repo. Of course, yeah, like you can of course just do this, but I want to like illustrate how you can do it when you want to contribute a model that doesn't have its model available on another hub like Torch Hub, because in that case you will definitely need to create a similar script like this inference.py script as I'm doing right here. But so yeah, they do provide these checkpoints here, like vision transformer based distilled backbone only. So let me copy this address, and then you can do state dictionary equals torch.hub.load state dict from URL. I know it's a long name. And then you can do like this. Typically you have to specify map location equals CPU. And then you can like equip the model with that state dictionary. So the state dictionary is just a regular dictionary in Python, where the keys are the names of the parameters and the values are the actual parameters values, like as torch tensors. So in this case, yeah, we want to equip it with the base pre-trained weights, and then we gonna load the state dictionary. And then, so let's say we want to do a prediction. Well, problem is we cannot really make a prediction of a certain class because they only have open source the backbone checkpoints here and not the actual classes, unless we load those models with a linear head, but they only seem to include the linear head weights here. All right, so let's load the cat's image. So for that, let me just quickly go to the Dino repo here, which contains that code snippet that we need. So this is just a standard image of those two cats chilling on the couch. Maybe let me make it more clear by adding some comments. So first, load model, equip the model with the weights, and then yeah, load image. Thanks GitHub Copilot. Oh, it's even already knows I want to use a cat's image. That's very nice. And then we want to, of course, yeah, prepare the image for the model. You cannot just forward your pillow image through the model. So for that, let me check what kind of pre-processing we need for this model. So data, transforms. They use this mean and standard deviation. make classification eval transform, resize, center crop. Okay. Well, it's a very standard way of preparing an image for a PyTorch model. So for that, let me import the transforms module from the Torch Vision package, and then we can say like transformations equals transforms indeed dot compose, and then we have a bunch of well, thanks GitHub Copilot, because I need all of those. Like typically when you want to prepare an image from a model, you will definitely like need to resize the image. You need, well, resizing and center cropping is not really needed here. Well, they actually use, okay, so resize size, yeah, to 56, and then a center crop. I think the reason GitHub Copilot knows this is because it's like watching the whole repo. It's pretty smart. Maybe to tensor, and then the mean and standard deviation. Okay, and then you can say like pixel values, let me call them pixel values, equals transformations image dot unsqueeze. Yeah, GitHub Copilot is really handy. And then we can just say like, let's just see what's in there. Well, let me also see maybe what the model is actually returning. So this Dino Vision transformer model. Forward features list, forward features, forwards. Okay, self.head. But yeah, this model doesn't include a head. Forward features. It's going to return a dictionary. XNorm ECLS token. Okay. Anyways, let me try that, and then let's see whether this outputs a dictionary. So yeah, this is like our basic inference script to just run our cat's image through the model. Proof script, yeah, actually those commits of course don't really matter, but, and then I'm gonna push again to GitHub, to my fork, not the Facebook research repo, but my personal fork. And then, yeah, I'm actually gonna need to move back here to the content folder. I'm not sure actually, I need to restart the runtime, but oftentimes, so let me call this notebook run forward pass original implementation. But yeah, this is typically what you need to do as a first step when you want to contribute a model. Run a forward pass on some dummy input data. So in this case, as you can see, we're currently loading the pre-trained weights of Dino V2, the base sized version, but yeah, there seems to be a mismatch. And I can already see, so there is an issue, bias, as well as, yeah, I think the reason is that the model that we are loading here, Dino fit base, let me quickly search that one. Okay, so they define it here actually. Dino V2 model, fit base, pre-trained on the LVD 132 million dataset. And then they have this make Dino V2 function. All right. As you can see here, they're doing actually the same thing. But yeah, they set the image size, they patch size. I can see, and then, yeah, so they import. All right. So yeah, image size is set to 518. Let me go back to the, right, so we're gonna need some, we're gonna need to provide some arguments here. Patch size being 14. Pre-trained equals true. Arc name. Init values. The feed forward layer. The block chunks, not sure what those are. And then yeah, pre-trained equals true. All right, so let me go back to the Dino V2. Okay, so they only changed the vid base, well, the arc name to vid base. But other than that, make Dino V2 model name. Oh, see, as you can see, they also use storage.hub.load state dictionary. All right, so let me provide those updates. Fix model, hyperparameters. I'm gonna push again to my fork. And I'm gonna rerun the script. I know it may seem like a hassle to like restart the runtime every time and rerun this, but actually for me, it's just a lot handier than having to install all the dependencies of a certain model. Oh, Dino Vision Transformer has it. Okay, so apparently this Dino Vision Transformer doesn't take a pre-trained pre-trained argument. All right, then I'm gonna just remove that one. I don't think it's needed. Gonna repush, I'm gonna restart. I don't actually know. I should check whether the restarting of the runtime is required, but oftentimes you need it to like make sure that it's using the right new updated version. So it's complaining Xformer is not available, but Xformers is just okay. So now we're getting our outputs. That seems great. So we have our xnorm CLS token. As you can see, these tensors are now coming out of the model. So what you can also, for example, do is like for key value in outputs.items, let's say if is instance of a torch tensor, then you can print out shape, else let's just print out their value. Okay, let me check whether it works without running. Okay, open new. Yeah, I can restart the runtime and run all. But yeah, so what we've done is just we've added a basic script to the repository. So we first forked it to our own name, and then we cloned it locally. We added the script inference.py, and then here I write like a very basic script to just do a forward pass with the original implementation on some dummy input data, being the cat's image. And then as you can see, this is what comes out. So yeah, we have this xnorm CLS token, patch tokens, prenorm. So those will be the tensors that we're gonna use to check like whether the Hugging Face model will return the exact same tensors and the exact same values on the cat's image. The only thing we maybe can do here as well is, because yeah, I've now created this inference script like on the fly, but we should check whether like it's returning the exact same thing as this one. So actually we can do this as follows. So yeah, they already provide checkpoints on the torch hub. like you can also do like the following. And then yeah, you can like do the exact same thing. So you can do like dot forward features. So like that's an alternative way to like do a forward pass on the cat's image, because yeah, we can just use the model that they already provide on Torch Hub. But so yeah, as I already said, most of the time you won't have this available when you want to port a model from another repository. Like oftentimes they don't provide like an easy to use API to use it. But in this case we were lucky because they already provided. So as you can see, it returns like the exact same thing. So you can also do for key value in outputs.items if is instance v torch.tensor print key v.shape else print key v. So yeah, like this is gonna return the exact same thing. As our script that we wrote. So now we are like quite familiar with how we can like instantiate a model. So there are basically two ways. You can either like do it as we did in the inference script. So you can like import it from this folder. And this is usually how you would need to do it if you are working on a random model that doesn't provide its model already using TorchHub or another kind of API. So then you would have to write a script like this to do like a basic forward pass, because this will come in handy when we want to like debug our implementation or Hugging Face implementation, because then we can like easily add print statements here to just see like, let me maybe do that. So for example here in the forward features method, you can just add a print statement like shape of the embeddings before the transformer, because yeah, like we can easily check what is the shape, for example, of the intermediate tensors, or we can easily check the actual values, and this will come in very handy when we want to like debug our Hugging Face implementation, because the idea will be to also forward the cat's image to our Hugging Face implementation, and then we're gonna compare those tensors between the original implementation. As you can see here now, it includes this print statement here, shape of the embeddings, and this will come in very handy when we want to debug it. And as you can see, the Torch Hub model doesn't seem to include this print statement. That's interesting. So yeah, that's another reason why we're gonna use this inference script rather than the Torch Hub model to debug it. But yeah, one thing I'm gonna just check, like one thing you can also do is like first values of x norm. So the shape was has 3 values, so we can maybe print out like those first values. And then I can run the script again, so just restart run all. As you can see, it's quite fast, so it's handy. So yeah, we can like, for example, see what are the actual values of this x-norm tensor. As you can see, it's like minus 131. So let's also do that for the, well, the problem is, okay. Or maybe let's see just So X norm. Well, this, wait. Yeah, I just want to see whether this thing is returning the exact same thing. So maybe let's just print this out. And then we will simply see whether our inference.py script is returning the exact same thing as this torch hub model, because that's like required if you want to make sure that the inference script is working fine and we can use it to debug our Hugging Face model. So yes, printing this out, and it starts with -2 and so on. And here, yeah, it also starts with the exact same values. Yeah. So yeah, usually when you see this, of course, you can also use assertions to like really make sure that it returns like the exact same values. But this seems to be okay. So yeah, now like we have our basic inference script, and we can like use it to start debugging our Hugging Face implementation. So yeah, this is like the first step that we now completed. So yeah, run a forward pass on the original implementation on some dummy inputs. So yeah, usually for a vision model, this could be like the cat's image. For like if you want to work on an audio model, well, just use one specific audio file and just use that to run it through the original model as well as the Hugging Face model. Yeah, some dummy audio file and so on. And yeah, this will allow you to like debug the Hugging Face implementation, which is one we're gonna do in the next steps. But yeah, I'm gonna do that in a separate video. So I hope you enjoyed this one, and yeah, next time we're gonna just make some further progress on porting the Dino V2 model to Hugging Face. See you there. Bye bye.